Okay, so well, I think we should get started because so on the screen at the moment, I think you should be seeing there's a list of the talks we have for this afternoon. So we've got about 90 minutes and we've got 7 talks plus maybe a little bit of time for questions. So I think the way we want to run it is kind of, we'll let the speakers do roughly 10 minutes. I'll be fairly strict on time so that we make sure everybody gets a chance to talk who's down on the schedule. And then if people want to put questions in chat while the talk's going on, then we should have time for maybe a couple of those questions at the end of each of the talks. And Charles kindly allows us to have a brief break in the middle. So hopefully we'll actually be able to have a break. We won't run out of time, but that gives us a bit of buffer. So I think the way we should do this is just get started. So Cherry, are you kind of ready to give your talk? Yeah, you're not, we should unmute you, yeah? I think.
Can you hear me?
There you go. Yeah, I can hear you. And I think the way this should work is you just share your screen, your presentation, and start. And I will kind of yell up at like 8 or 9 minutes to let you know. Okay.
Yeah. I don't see the button to share it because you're sharing, or
maybe I need to stop sharing mine. Maybe that was my fault. I've just did stop sharing. Do you see the screen share at the bottom?
Oh yeah, I see the screen share now.
Okay.
Okay.
Great.
Can you see my slides now?
Yes, you're kind of in. Yep, that's it. Yeah, that's perfect. Looks good. Okay. Get started.
Okay. Good afternoon, everyone. This is Fang Cherry from Georgia Tech Pest team. I'm going to give a talk on data analytics and the Provenance tool development at the Georgia Tech Pest Center. Okay, so today I'm going to cover 2 software frameworks developed at Pest. One is a scheduler data analytics tool called the Pest Fact. And this is a joint effort with Texas Advanced Computing Center. We built a streamlined log data processing pipeline. And the second tool I'm going to cover is a Provenance-based benchmark suite called the Pest Prevention. And this tool is currently publicly available at GitHub, as the link states. And we basically want, this tool is a planful independent tool, which can help us quickly set up the test suites and collect performance data and preference data for like a few further data analysis. First, the Pest Fact. So the purpose for this tool is we want to use a big data processing tool, Apache Spack, to speed up the processing. So, and also we want to reduce the data in great well so that the user can use the data in the local laptop. We also want to gain the insights into the researcher's behavior using the data we got. And this tool is written in multiple program languages, Java, Scala, Python, and Bash. And the data is generated daily, currently to facilitate up-to-date analysis. Okay, here is the workflow for this framework. So at the top is the PBS2 database. So our analysis all based on this data source. So PBS2 basically is a tool to collect all the user jobs through the scheduler logs. So we can capture all the job-related information, including the scripts people used. And for Pest Fact, we just we have a 3-part: pre-processing, middleware, and post-processing part. So the pre-processing part is we first do a daily data collector from the PBS database, and the data collected will put as a JSON format in the shared file system, and then we will pre-process those data. First, convert those JSON data into Parquet, which can facilitate speed up the processing. And then we further process this Parquet data to generate a CSV. So at the bottom line, you can see the data we got injected is about like 20 gig in total. But after pre-process, the data size can down to the 600 megabytes. And we further reduce the data sets into doing the middleware layer to make sure it can run even faster on the post-processing part. So the middleware we written in the Scala format and in the Scala language, and then we just based on the customize the data in the CSV file to the post-processing. So the post-processing user can do it anywhere, and especially for those who want to do some visualization type of work. Okay, so currently by using this Apache Spack, we gained a huge performance improvements. So previously the couple of hours running time can be reduced to several minutes. And also we've dramatically reduced the data sets, which can facilitate further analysis. And using this tool, we can understand and our researchers' behavior, and also it can give us a lot of meaningful action items. For example, we have this software usage tier analysis. So we rank the software used most as a tier 1 software, which can get most of our attention. But for the less used software, we will have less support to it. It can benefit our manpower to the most critical task in the team. So in the past, we also past a couple of years, so we have a couple of papers surrounding this work, and feel free to check out those works and in the papers. Okay, so this is a sample outputs from PaceFact. You can see the first table usually is on the stage. We have a 600 megabytes. So we can see we still have a lot of redundancy of the data, for example, usernames and the groups. And the second table is our down to the 5 megabyte data size table. So in here, we get a further aggregation on the data. For example, we don't care the software version anymore. We just simply do, okay, for Abacus, we just care about how many users use it and across how many groups and how many jobs has been run during last year, things like that. So we can further reduce the data and for the post-processing needs. So currently we are still continually produce the customized data sets for the downstream analysis. For example, currently we have ongoing internal user editing. The PaceFact data helps us understand a lot about the user's usage. And also we plan to integrate more data sources. So far we have a PBS2 data source integrated, and we plan to integrate LMOD and XOR data as well. So LMOD can give us some detailed information about the default module user put in their bash scripts or in their module files, in their PBS scripts. So XOR can help us understand more about user software usage, about user self-built tools. For example, currently the PACE virtual environment. So for example, the TensorFlow they build, we need to understand how many people use TensorFlow. If they build it virtually by themselves, we cannot tell the result, data right now, but with XOR, we will be able to find out. So that's 2 data sources we plan to integrate in the near future. Next, let's take a look at the Pest Prevention. So this prevention is mainly based on our leads. We want to quickly set up a test suites, and that suite has to be platform independent, can live with any existing software stack, and also we want to consistently capturing those testing data so that we can rerun the test and without any questions. So this framework is written in Python and Bash. So this is the architecture of the framework. So this is mainly the layered and the componentized design. So at the bottom layer, we have this database, Provenance database, and the middle layer is the whole part, the middle, the main part of this framework. So we can see for each experimental component, it has 4 different other components associated with this one. So for example, the results component, we have this at the bottom. So that results component has a file-based results and query-based results. So the file-based results mainly for the debugging purpose. So you can quickly get results whether or not the test runs successfully or not. And query-based results is the full details and with problems data and push into the database, which can allow you to test it and query it later. For the runtime, we want to support both interactive run and the query run. So this is very common in the HPC center. We have to allow user to run the test in 2 different ways. And the system component is very important for this performance comparison test, because we always have, okay, exactly 2 input file, exactly same software stack, but they behave differently even on the same hardware. So we need some information to understand why that happens. So those system information needs to be captured during each testing we are running so that we can do the comparison in the future. For the application, as well. So we need to test, okay, what test case is this application used, and how we compile the source code, which flag we use to compile the code, and how we run it, which is the like version and the dependent tree, all the tool chain, how we use that. So we want to collect all those detailed information to make sure we identify the application we are using in the future for the testing purpose, for the comparison. At the top level, we have these two user interface components. One is allow user to run test, and another is to query the test. So during the whole, we also integrate the Lawrence Livermore National Lab Spack into this framework for the automatic tool chain build, which is saved us, like speed up the tool chain build a lot for us.
So Cherry, you're down to 1 minute, okay?
Oh, okay, so the usage, okay, so this is just two simple usage you can use for the test. And this is the output. After you run the queries, you can get this type of outputs to do the further analysis. So basically, this can give us a quick way to do anything for the benchmark. So in the future, yeah, we have a paper submitted to Supercomputing 2020. We want to promote tool to the community and add more functionality as well. The conclusion, so both tools are actually used at a pace right now. So those tools reduce dramatically our manpower in the daily base. And we want to promote this tool to the community. Anyone interested in using this tool, feel free to contact me, or we can continue discussing in the US-RSE Slack channel for the further collaborations. So we can build this tool towards to some grants in the future. Thank you.
Thank you. That was very, very interesting and perfectly fitted within your job slot that we allotted for you. So that's good. So well done. So any questions? I didn't see any in chat. So I don't know. I had one, which was just, I was curious how you mentioned you were doing things against PBS. How tightly coupled is your kind of logging stuff to PBS, or could you plug in some other scheduler there, do you think?
Oh, yeah, you mean the scheduler. So basically this we are more based on the data coupling. So it's more like PBS tool generates the data.
I see.
Are you talking about the Pest Fact or Pest Prevention?
The first one, Pest
Fact. Pest Fact? Yeah. So Pest Fact, when we do the coupling, we have like just through the database. So PBS tool has a database. We just acquire the data from the database. Ooh. So this as long as the data as long as the data format looks right, there's no kind of differentiation between different scheduler yet. Actually, that tool was originally being used by Texas Advanced Computing Center. They actually process the XOR data there. But we work together, make sure they work with our PBS tool data. So yeah, as long as we can supply the schema, yeah, the tool can handle that. That's not an issue. Yeah.
Excellent, thank you. Okay, so let's move swiftly on so we can get our next speaker in. So the next speaker is Junchao. I think that's pronounced right, I hope, from Princeton.
Yep.
Yep, you're there. And do you want to share your screen? Are you able to do that?
Yeah, so I'm sharing my screen right now.
Okay, and I think this is a different level of things. You're going to talk about a cryo-EM package, is that right, or something?
Yeah.
Yep, excellent.
So can you see my screen now?
Yeah. So again, I'll give you a kind of 1 minute warning, and then you'll have to race the end. Yeah, does that sound good?
Okay.
So we'll start. So I'll start my 10-minute clock when you go, and then. Okay.
So good afternoon, everyone. So my name is Junchao Xia, and from the Department of Research Computing at Princeton University. So I'm also working with Professor Amit Singh in the program in applied and computational mathematics. So today I give a very short introduction of our work on development of a SpirePython package for reconstructing 3D density map, of biomolecule from 2D crane images. So traditionally, the crystallography is the popular way to obtain the 3D structure of biomolecules such as protein. And the crane was invented in 1970 and became popular recently. So in a very short, the high-speed electron goes through a thin layer of biomolecule solution, which is vitrified at the liquid nitrogen temperature. And some of the electrons are scattered and detected to form 2D images on the micrograph. So since we are interested in the native structure of a biomolecule, so we have to use very low dose of electron, so to reduce the radiation damage. So the 2D image we obtain is very nice, as shown in this picture. So the resolution of Korean structure used to be very lower, roughly 20 angstrom, but recently the revolution of resolution happened in 2040. So due to two major contributions, the first one is the new development of the direct electron detector to count the number of electrons projected on the 2D screen. So the second one is the new development of the computation method and the software package to build a 3D density map. So for example, as in this science paper, scientists were able to release the first high resolution structure of novel covalence spike protein, glycan protein that binding to the ACE2 receptor of a human cell. So just 1 month after Wuhan city is locked down, so that is very, very quick study. And this used to be take several years to glow the crystal and using X-ray to resolve the structure. So what is ASPIRE? So ASPIRE is a short name for algorithm for single particle reconstruction. So yes, the original ASPIRE MATLAB package was developed by dozens of short-term graduate students and postdocs. Currently, they consist of more than 100,000 lines of code and covers almost every step of ab initio reconstruction of biomolecule. The development of the original MATLAB package was a single purpose, the prototyping the novel ideas and proposal new algorithm for cities and publication. Currently, there are more than 40 publications right now since 2008. So the original MATLAB package was developed in a very free style. This leads to many challenges for user and developer. For example, the several sub-module package exists, but with problem of redundancy and compatibility. So there are no formal documentation for user and the developer. Due to this problem, so line-to-line converting is not a good practice. So we are developing a new Python package. There are tons of the software package for analyzing the Korean data. So why do we still need ASPIRE? This is because ASPIRE has many unique features as I list on this slide. So flip from the fairly basic functionality, such as automatic particle picking, to more advanced algorithm on 3D covalence analysis to address problems for molecular heterogeneity and structure variability. So generally speaking, the related algorithm was proposed by mathematicians and have more rigorous mathematical representation. So however, the accessibility is critical for the long-term research goal and external usage. So we are developing the new Python package to address this problem. So currently we have the 3 RSE working on the new Python package. So Vinny started his part-time job in the middle of 2018, and I started my full-time job at the beginning of 2019, and Greg just started his full-time job in the middle of the last month. So each RSE have the individual sub-module to convert and to work on with, but relatively independent to each other. So last year, my job is was converting the Cover 2D module for denoising 2D images. In addition to the converting code, I also have additional duties such as perform the literacy survey to understanding the details on algorithm and discuss with researchers and RSEs every once per week for a few months to building the new framework as shown on the right chart. So we also redesigned the Spack architecture using the top-to-down method and reorganized the existing code and re-implemented new code by OP style. So this slide shows an example how we reorganized, re-implementing the code by OP design. So currently there are more than 6 scientific papers proposing different mathematical function to do 2D image expansion. So this graph shows you how we re-implementing the mathematical based function using the class hierarchy structure. So in addition to day-to-day code developer, we also participate the 2019 Princeton GPU hackathon to improve the code performance for the sub-module Apple Picker, which was developed to pick millions of 2D particles from thousands of micrographs. So this graph shows the total clock time to finish all 84 micrographs as a function of developer iteration during the hackathon event. So there's a lot of information over there, but in short, for the original Python package, it needs 80 per micrograph on one thread of CPU. After we implement the GPU code using CodePy and other libraries, we were able to reach 4 seconds per micrograph on one thread CPU and one GPU. That was 20 times faster. Even more, if we combine the multiple node GPU nodes with multiple CPU on the Tiger cluster, we can reach the 1 second per micrograph. Yeah.
1 minute, okay.
Okay, we can reach 1 second per micrograph. So that's almost 18 times faster. So in a summary, so we are developing a minimal set of a Spack package. So we hope we can finish in this year. So finally, I would like to thank Mueller RSE from the Research Software Engineering Group led by the Ian Coston. I also would like to thank Mueller postdoc and graduates from the research group. And I would like to thank many others listed over there, but cannot mention one by one. Thank you very much.
Thank you. That was very interesting. I enjoyed that a lot. So thank you. We had one question posted that was from Casper, which was, what was the biggest challenge in terms of software development in trying to build this new framework from starting over? Would you say?
So I think that the most challenging problem is that the package was developed since 2008. So there's many people involved, but already left the group. So sometimes you cannot find the right person to show you what exactly is the code to do. So in this situation, so we have to go back to the paper to read it, to understand what is that, and then figure out by yourself.
Yeah, that sounds like a familiar story. I think other people may recognize that. So I'm just looking for Pradeep. Are you on the call? You're the next speaker.
Yes.
Okay, good. Hello, nice to meet you.
Hi. Very nice to
Yeah, so our next speaker is Pradeep, who I believe, are you in Canada? Did I get that right, Pradeep?
Yes, Toronto.
Yes. Okay, so you're our international participant in that sense.
Oh, yeah?
Yeah. So welcome. So do you want to try sharing your screen? I think, I don't know, we have to stop.
I think, yeah, the previous speaker must
Yeah.
stop.
So Junchao,
Yeah.
I think we need to do some sort of stop, or maybe one of the hosts can do it. I don't know. Can you stop sharing somehow? Oh, you're trying. We can see you trying to get out of Zoom. So.
Can I stop? Oh, okay.
Yeah.
I think you might.
So unshare, I think. I don't know.
I cannot see the unshare screen.
When you click on Zoom, just press escape. It will bring the menu.
Zoom, okay, Zoom.
So I shared my screen now.
Oh, okay. So Sandra's done it. So now, Sandra,
Okay.
if you unshare, I think, or
And
something.
now I unshare, exactly.
Yeah. Excellent.
So,
Okay. Pradeep, do you want to try sharing now? And then we'll
All right, yeah.
move on.
so I can take it away, yes.
Excellent.
Okay.
Okay, no.
Yeah.
Okay. Well, take it away, Pradeep, and I'll give you a 1 minute warning in shortly.
Yeah. Thank you. Thanks everyone for joining. Thank you for the organizers for letting me sneak in to the US borders here. So today I want to briefly discuss a library I built to make my own life easier for my research data management, especially for biomedical data. I call it Pyradigm, to look it up later too easily. So anyway, we all know the difficulties in data management, even for your own documents on your computer, to like large set of diverse mixed types for your research analyses. And you probably have seen graphics like this as in the context of research data management. This library is not gonna solve all the problems. I do try to reduce data entropy, as they call it, in few parts of the life cycle for few parts of the research data, right? Specifically like analyze, preserve, share, and reuse. They sound too broad and very applicable, but I'm going to focus on small subset of problems that I work on. But I think the ideas are generally useful for other domains also, right? So my life revolves a lot around tables of data extracted from images and other types of data for machine learning. So this library does not deal with files at all. Right? Typically, that's what people think about as part of research data management. But we don't stop with files, right? We create new features and files with them, and then there is a recursive need for data management, right? So typically my life cycle related to these data sets revolves in this space, typically either input or raw data, for example, MRI brain images or EEG data, for example, and there are several layers of intermediate data followed by several variations of outputs data, right? So depending on the scope of the analyses or project we're working on, we'll have to slice and dice these intermediate and output features in various ways, which means the tables gathered and assembled from various sources. And you can see that things can go easily wrong if you don't take great care in making sure you're doing this properly. So as challenges specifically for medical data or biomedical data I deal with, there's like tons of tables. Like anytime you want to do some reasonably useful interdisciplinary analyses, so which means that there's mixed data types, both for primary features, which are the numbers, as well as the secondary features associated with them in terms of demographics and other types of features. And there are several attributes to them too. And because you need to link multiple tables with unique IDs, often actually linked by the patient ID, depending on the type of the analysis, it could be something else too. And you want to try capture provenance as much as possible, especially in terms of processing steps and their metadata like command line arguments, parameters, etc. And trying to achieve these with ad hoc scripts is not fun. You know, maybe okay in the beginning when you're trying to learn how to use scripts and how to play with CSV files, but as part of a day-to-day analyses, when you have to work at tight timelines, this gets really boring. And because data and scripts change hands quite frequently between students, RAs, and staff, etc., with limited training both in software as well as data, errors can creep in easily and they don't get detected as well unless something blows up, right? So I would call that a recipe for disaster. And we're trying to basically reduce the chances of that happening with centralized data structure where there is some sort of basic validation going on as you populate and integrate data from multiple sources and reuse it, right? So, yeah. Moreover, if you, for example, like one might say, you know what, why not use pandas or Xarray or something else instead of a CSV file to try reduce that pain? Well, what I found when I tried to do that was that using these libraries, there was some like barrier of cognitive burden in terms of understanding what certain things mean in these data structures, and sometimes they can be too contrived. Terminology is confusing sometimes, leading to mistaken use. And often you need a little bit more adaptation for your own domain in terms of how you name, validate features and values, and how you deal with different types of diverse attributes you're dealing with, right? So in order to try make it easier to use and manipulate, but also reduce the data entropy over time, because you know data lasts much longer than the project itself, right? So you want to try make it as easy as possible while retaining the information as precisely as possible. So this data structure, like I called a paradigm that I built, essentially the core is, like I said, it's a table of features. Think of it as some sort of input to scikit-learn for machine learning prediction, right? Like in the machine learning world, people often think of it as capital X. You know, you may be familiar with that as you read tutorials. It is basically n rows and p features, so to say, right? But life is not just that. People often have to deal with targets. The thing that you're trying to predict. You know, is it like healthy or disease or something else? There can be multiple values sometimes for advanced applications. And moreover, each of them actually have a set of attributes also. And these targets, attributes, and features must all be linked to a common ID, so you don't mess up, right? Because mixing up data from patients and healthy could be bad. You know, you lose invalid results, and debugging that would be a pain if you don't take care of that properly, right? So basically the library is built such that it makes it easy to populate various types of data, as well as slice and dice it in any number of ways, while propagating all the metadata and other basic validation that's happening behind the scenes. So what it is basically there's an abstract base class. This is all done in Python, by the way. I'm a huge fan. I love it. In fact, it would not be possible without Python. I come from the MATLAB world. I think based on the previous talk, I agree with everything I said. We couldn't do this in MATLAB. So this abstract base class defines the course structure and properties as a collection of hashable IDs, each ID expecting data as in features as well as associated attributes and a target, you know, for in the machine learning sense, and an optional set of attributes, which could be metadata and whatnot. And this lays down certain basic validation depending on what type of data that is being added to it. This is very helpful because it helps catch errors early. And if this data structure comes with a large number of convenience method in terms of not just adding samples, but also summarizing, deleting them, and combining them in an arithmetic fashion, you know, as well as sampling what's inside the table, which can be quite useful for machine learning, and to export it into different format depending on your needs. More importantly, what I actually use is are the derived classes like classification data sets.
1 minute, if you can.
Whoa, okay. Regression data sets. So this lays down some criteria for targets in terms of categorical and numerical. And there's many other possibilities for your own needs, right? So maybe I can skip some of more implementation details. Basically, this is a quick snapshot of how it is used. The top few lines populate the data structure, just go through IDs, add features and data, and then you can add attributes and some other metadata. This would make the data structure pretty self-contained and self-explanatory for other people who wants to use it, right? Instead of just putting comments in a CSV file. Like I said, you know, data sets can be combined and subtracted or transformed very easily without having to do lots of loops and redoing it. So it saves a lot of time, makes it intuitive and productive, which otherwise would be a huge pain if you were to do it with CSVs by themselves.
So I'm gonna say,
yeah.
Should we tell everyone? I think that's a good point to pause, because okay, is that okay, Pradeep? Just so that we give other people.
Yeah.
So we've got a break coming up. I think we could have a question, or I've got one question I can ask. Yeah. So your stuff's on GitHub and people can read about it there. Should we say we'll start again officially at 3:45? That'll give us just enough time to get through the remaining 4 talks, I hope, if we're disciplined. So, so let's declare we're starting a break. But in the meantime, I did have one question for you, Pradeep. I don't know, is anyone else? Nobody's posted a question, so I'll ask this one. I was curious how you decided on the right data structures. Did you have a background in the field you're in to sort of know, or was it kind of experimental and you spoke to people?
Data structure as in the design, you mean?
Yeah. Kind of how you split things up and kind of.
So I've been doing this for a long time. I originally built something similar in MATLAB to make my life easier, because early on, after making big mistakes, I learned that the hash, the unique ID that needs to link everything together, it needs to be maintained properly, because I made mistakes, leading me to build predictive models that are 100% accurate. You know, they don't exist. So this design developed over, I would say, 6 to 7 years of me having basically starting with scripts and adding more and more conditions and validations, and that I distilled that into this data structure. So this is probably like the 4th rewrite of the data structure. Does that make sense?
Yeah, it does. No, I mean, I always believe that some of these things are a process of iteration and discovery as well as design. You know, you kind of have to try.
Yeah.
And it's always takes longer than people imagine for the right kind of.
Oh yeah, this is like 4 times rewrite. You know, in fact, I didn't touch on another aspect here. I think you can still see my screen, right?
Yeah.
So once you have the single data set built, like I showed, what happens really in actual research projects is that you have many such tables that you need to link together. Like, for example, something called multiple kernel learning or whatnot. And if you want to make it efficient, because there's a lot of information that's redundant in terms of targets and attributes, right? So I use that to derive something called a multi-data set. And this not only is space efficient, but also it reduces the chance of making mistakes because you're reusing, right? The same with software, right? As the more you use, the less likely that you make mistakes in a particular algorithm implementation, right? So, yeah.
Thank you. Okay, so we'll continue with our break for another 4 minutes, and then we'll get on with Sarah from Harvard.
And I will go to the next slide on our little Menti poll. So if you would like to answer on the slides, that would be also great. Thank you.
Do you have some, Sandra, do you have some intermediate results you can show of the polling while we're?
Oh, yes, I can do that.
Yeah, that would be great. Why don't you see how we're doing? So we have 62 participants, so we'll see if everybody answered or not.
So we have 28 answers.
Not bad.
That's great. So I can let that go through and switch then to, after the break, to the next slide.
Okay, I'm going to go and grab a coffee quickly.
Can you hear me okay, Sandra?
I can hear you now, yeah?
Okay, great, thanks. Just wanted to check my mic.
Yeah.
Also, this is Casper. Just want to see if you can hear me.
Yes, I can hear you.
Awesome.
Hi there, this is Chris Stone, just doing a mic check.
Yes, I can hear you.
Excellent, thank you.
Thanks.
Okay, I'm back. Sandra, are you back?
And I'm back. And now we have 52 people who have answered the poll. That is very cool. And it's very diverse from, you can see conflict resolution to neuroscience, HPC, physics, health, biomedical informatics. So we have a really diverse group. Social sciences, that is good.
What was the other question?
Go now to the next slide, so it will be up in the background. And it asks, what kind of institution do you work at? So that would be great if you answer also this. And I stop sharing.
Excellent. Okay, great. So, Sarah, are you out there?
Yes, I am. Should I go ahead and share my screen?
I think so. I think if you're ready to go, we're ready.
Yeah.
So,
okay.
We'll give you your 10 minutes. And we'll see if we can fit it all in. Thanks.
Okay, sure. Okay, everyone can see it?
Yep.
Okay, great. So I'm Sara Leinicke, and I'm an RSE with Harvard University at the Faculty of Arts and Sciences Research Computing. We all heard from Mahmoud, my colleague, earlier today. And I'm going to be talking about the development of an automated high-throughput animal training platform. So just to provide some context for this project, we are working with the Ovechki lab. You can see the PI on the left is Spencer Ovechki. He's a professor of organismic and evolutionary biology. And he researches neural circuitry underlying learned behaviors. So this requires researchers to train animals in controlled sensory motor tasks. And the challenge with this is that it's very time consuming. It's labor and resource intensive, and it's subject to human error, human biases. You can imagine if you trained, say, a rat to do a particular task, like touch a lever twice, you might do it differently than you did it yesterday, and you might train it differently than your colleague. So this kind of presented some bias, and it was also difficult to scale this type of research because it's so resource intensive. And so the solution that we came up with was to automate this process using an automated training system. So as you can see in this image, instead of having an RA or a lab tech manually train a subject, here a rat, in performing the sensory motor task, like touching a lever, for example, instead of having that person, train one rat manually and then move on to the next, we see a software, like an RA using software to train a bunch of rats. So this gives you an idea of how easily we could scale the system. So if you can see kind of in this picture, the hardware that's required for this setup. So we have teensy microcontrollers that are monitoring events like touching levers or touching the water bottle with your nose. There's Raspberry Pis that orchestrate the training instructions and receive and pass on logging information from the teensy microcontrollers. There's also Pi cameras on each box. So while the rat or the subject is executing behavior, as part of this training methodology, there's a Pi camera constantly recording video. And this is all done with open source tools. So the back end, we use Python and C. We're wrapping that in a Flask server. And then for the web interface, we're using Vue, and we're using a Postgres database. And the results so far have been very comparable with the traditional manual training method, but it's a lot less expensive. It takes a lot less manual training time, and it really lets the researchers focus on the content of their research rather than focus on carrying out these training sessions. So this slide gives you an idea of how easy this is to scale. So on the left, I have a video of a subject like touching a sensor with its nose and then getting rewarded. In the middle, you see this rat box scaled up to 6 different boxes. And on the right, you can see inside these closed doors are many, many rat boxes. So the lab currently has 207. So it's very easy to scale. And I wanted to talk about how we actually go about training these animals, like how the software does this. So what we have, and this is like very simplified, but basically we have state machines that define training sessions within certain time periods. So in the top left, this image gives you like a very simplified idea of how this works. So there's 3 different tasks that get increasingly more challenging. So the first, like on the left, you have tone conditioning. So this state machine would orchestrate an event pattern where the rat hears an audio cue and then learns that that leads to a reward. And then once it successfully has learned that task, that sensory motor task, it moves on to a more complicated step and more complicated state machine. Here it's trial initiation. So the rat touches the lever and gets a reward. And once it learns that task, it moves on to the more complicated task that the researcher is really interested in, which is moving the lever left and right, just as an example here. So we get a sense with this example that the state machines really serve as modular, reusable training tools. So researchers can share the state machines that they have developed with each other and get to the point where they have trained these subjects in these increasingly complex tasks. And on the bottom of the slide, I talk about how researchers are able to analyze whether this training system has been effective. So there's two main sources of information for them to look at. And one is the microcontroller logs, so the teensy logs of the input, analog and digital input and output, whether the lever was pressed in a certain period of time, whether the bottle was licked in a certain period of time. And then they also have the camera files. So we are continuously recording camera, but only saving camera files, starting right before an event happened up to after an event happened. And they can look at all of this data to get a sense of how effective this training protocol has been. So on the left, we see what they use primarily, which is an accuracy diagram. And then in this example, we have 100 hours, the rat has learned 20, a little bit more than 20 stages. So stages are basically composed of state machines. And then I wanted to present just some examples of complicated sensory motor tasks that this software system has been able to train rats to perform. So on the left, to tap, the rat is tapping a lever twice and getting a reward. In the middle, the cued nose poke, the rat is touching a sensor with its nose and getting a reward, after an audio cue. And then on the right, there's an audio cue followed by a lever press. And so there's two things that I kind of wanted to emphasize as we look at these fun videos. The first is that because the researchers use not their own manual methods, but because they use software like the state machines that I talked about in order to train the rats to get to perform these tasks, they're able to share their methods with each other very easily. And then, for example, if one researcher developed 2-tap and I am interested in using that for my research, I could take the 2-tap protocol and tweak it for my own use. So it really helps researchers build upon what everyone else is doing. And the second thing to point out is instead of having my lab notes on how I manually trained a rat to perform a task, for example, and with lab notes might be prone to more human interpretation or bias, researchers have automated logs of all of the events that happened leading up to this ultimate training result. This is the system diagram to give you a sense of everything that's involved. So on the bottom left, we see the user sending experiment data, and that includes the animal training state machines that I talked about into the web interface, into the view client, which then goes onto the Flask server. The Flask server stores some of that data in the Postgres database, sends the training instructions onto the Raspberry Pi, which coordinates these events, training event commands with the teensy microcontroller. The teensy microcontroller is reading digital and analog input and output from the rat training box. In this example, there's 2 cameras. You can have more. There's a master and a worker. These are Pi cameras sending video and audio files back to the Raspberry Pi. And then the Raspberry Pi is funneling these video and audio files and the event logs to lab storage where users can access.
Okay.
Yeah, I'm almost done.
Yeah,
access directly. And then it's also, the Raspberry Pi is also storing summary data. So the very important training events that happened, or the most recent screenshots from the video files on a daily basis into the database, which the user can then access through this web interface. So the meat of this work is all done, the backend, the Python and C, the hardware integration. This is all finished and it's been used and very effective. What we're working on now is creating a web application so that users don't have to use the command line to use the tool. So we're integrating this Flask server and the view client in order to, like I said, make it easier for users to access this. And the final final slide of the acknowledgements, I wanted to acknowledge Mahmoud, who wrote the software for this program, and then Sasha Leo in the Ovechki lab, who developed and configured the hardware. So if anyone has any questions.
Thank you. Great.
Mm-hmm.
I'll ask a question unless somebody else chips in. So my question was just, I was curious how the sort of process of debugging and testing this sort of infrastructure compares with, you know, more kind of non-hardware related software that people usually, you know, more commonly, I think a lot of us work with.
Yeah, so I don't know if Mahmoud wanted to contribute to this answer, because he actually did all of the testing. I've come on to the team pretty recently, but he had actually his own box with a rat once he got to the point that he was like comfortable taking it there. Yeah.
Okay, cool. Thank you very much. I think we'll go on to, I think Casper is up next. So Casper, I think if you can unshare your screen, Sarah, and then Casper, you can share. And,
sure.
We'll get going.
Waiting for,
yeah, I think.
Sorry, where's my,
finding the right button.
Stop share, okay.
Excellent. Casper, do you want to try sharing now?
Sure. And then let me know if you can see this.
Not yet, but let's see.
Okay.
Still see you at the moment.
Okay.
Let's see you.
Can you see it now?
Nope. There's.
Nope.
You see a thing that says share somewhere. Normally it kind of highlights a window and then you have to click share. Yeah.
Okay. Let's see.
Oh, that looks good. We're getting there.
Okay.
Yep.
Okay. You can see it?
Perfect. Okay.
Awesome.
Off you go, and I'll give you a 1-minute warning. Okay.
Sure. Thank you. Yeah, thank you for the organizer to let me present here the software about renewable energy integration. My name is Kaspar Mueller. I'm a research software manager at Intellectual Ventures in the Clean Energy group. And before I start, just want to say that the things that I present here is done in a team, so that's not all my own work. And at the end, maybe I have time to talk about the team. I'm going to start with the motivation, and then move over to the model. And I will mainly focus on the software framework that we have built so far, and I will also show some results. And at the end, talk about future projects and conclude the talk. So there are a few challenges when integrating renewable energy into the United States electrical grid on a large scale. And these two that I show here are just a few of many more. So on one hand, renewable energy on the left-hand side, as you can see, is wind power is unpredictable. So the wind power output is not exactly as predicted. And as you all know, when we generate electricity, we need to produce as much as there is demand in each instance. On the right-hand side, we have 3 different power outputs from solar plants in 3 different days. So rainy day, sunny day, and a cloudy day. So these are just a few problems. Other problems are like that we have a transmission system that is not optimized. So in this can cause congestion. So transmission system is not optimized. So it can cause curtailment. Curtailment means that we produce a certain amount of power, but this power cannot be delivered to the user, or it's just too much. And this is called curtailment, basically waste of electricity. So how can we get rid of congestion? That is, we can build more transmission lines, but there are some other hurdles there. There are regulatory issues, the not in my backyard mentality, it's very costly to build the transmission lines in the ground. There are political issues and special interest groups like the coal lobby that just wants to keep the status quo. On the right-hand side, you see two plots on the top. This is the power output from the different generator types. The red line is the demand, and above the demand is the curtailed power that's basically wasted. The bottom plot, we can see congested lines on the western part of the network. So to study this problem, we have started building a model that basically replicates the power system operation. And to do so, we first need some resources, some demand data, and an infrastructure. And we were thankful to Texas A&M, who has built a synthetic network for the United States that we can use. We only want to use open source data, and the reason for that is that we can share the output. It's not just a black box as many other softwares are, because there is proprietary information in this network and classified information about where the locations of substations and such. So this is a synthetic network that we were able to take over. So now to run some scenarios, we need a simulation engine. As mentioned, we mimic the power system operation. We take hourly time series. We run hourly time series simulations. And I'm going to talk more about this part in the next step, where I talk about this simulation framework. Now, the user can input some information about future scenarios, like renewable energy, like how much renewable energy will we have in 2030, about transmission line upgrades, if we have new technologies coming like storage and so on. So the simulation framework grew over the time. When I started off 2.5 years ago, it was just the principal investigator and me, and I kind of started bringing in the simulation engine, which consists of a power system model, which is written in MATLAB, and the package that we use is an open source package called MATPower. And we put in some input data, and we have to run an optimization problem, which is solved by Groovy, and commercial optimization solver. Now, in the meantime, we started building a data gathering package that gathers all the data, puts it in the database, and then we have a simulation handler that takes all inputs from the user. And then when the simulation runs, it goes into the analysis and visualization. A bit more into details. So we have built these Python packages for the data gathering part. So we gather network data, electric. That's all input data that we need. We clean it, so impute missing data. We format it, the whole story. And so the data that we have is hourly power output, hourly demand, grid topology, and generation location and capacity. On the visualization side, we have to translate output data that comes out of the model into meaningful output values. So we analyze this output, then translate this in transmission congestion, how much carbon was emitted in this electricity production, curtailment, and we show all kinds of plots we can see later. Then the simulation handler is the last piece that came about. We wanted to give the researchers a better tool to run simulations. So the user can create simulation by using the collected data, give some inputs. There is some scaling functionality to scale up to future scenarios, so it can scale demand for future years. And then can you execute the simulation, which then runs the simulation engine and can check the state of the simulation. And lastly, the simulation engine, which is, as I said, written in MATLAB. It translates the power system model into a linear optimization problem, which is then solved by the commercial solver Groovy. As I said, we would like to go as much open source as possible. Optimization solver there, we just don't have a powerful solution for that. As you can see, the next slide, some specs and performance. So we run here 1-year studies which have an hourly resolution, and to run the whole United States, which consists of 82,000 nodes and more than 104,000 branches. It takes us 30 hours currently to run that. And a fun fact here, as you can see on top here, the United States electrical grid is composed of 3 networks that are very loosely interconnected. So the Western, Eastern, and then Texas. Obviously, Texas wants to be able to be independent. Here's some results. I don't want to go too much into details. These are some visualizations that we have made with the package. But just to explain a bit, so on the top here, this is Washington. On the bottom is California. Watch out, there are different scales. Obviously, California uses more electricity, but and both states have ambitious goals. State of Washington wants to go to 100% clean energy in 2045, and as we can see here, we can reach in 2030 a sub-step by 80% clean energy. California has some troubles here, has to import electricity and has a lot of curtailment. Next up is transmission line utilization map and the curtailment map that shows where we can show where the transmission line is congested, where we have curtailment. And the last result here is we can also show that the price of electricity can vary a lot if we have a lot of congestion here on the left-hand side. On the right-hand side, where we have almost no congestion, there is no much price difference. Now, about the future, we want to build in data stream monitoring. We're working on a web interface for data visualization, and we also want to work on an input user interface where the user can input scenarios. And also in terms of moving more towards Julia, moving more towards open source data or open source project. So we're moving the MATLAB part into Julia. So as said, the team consists of 10 people now. We have research software engineers, research scientists, data scientists in the team, and we are hiring. So if you're interested in this project, let me know. Thank you very much.
Thank you. Perfect timing as well. So that was great. So, so Charles has a question that was similar to mine. You said it took, I think, 30 hours to do the whole US. Is that like on a single computer or just a standalone like workstation? Or?
This is on, so the bottleneck is the optimization solver, which is the commercial solver. This was run on an 8-core node.
Okay.
So yeah.
But it's not like a huge problem in some,
no, it's not a huge problem. No.
Yeah. Interesting. Okay, thank you. No, that was very interesting and a nice different topic from some of the others. So, okay, so I think next we have Todd. Are you on there somewhere, Todd?
Yeah, I'm here.
Okay, so Casper, if you can kind of
detach
yourself, how we do that, and then Todd can see Todd. So yeah, do you want to try sharing, Todd?
Okay. Can people see this? Maybe not. Oh, okay.
Yep. Okay.
All right. So I'm going to talk about Spack. It's a package manager for supercomputers and also for your Mac laptops and maybe Windows sometime in the future. This was sort of a project born out of anger. This is how I install things on my Mac laptop. I just say what I want to install, like NumPy, and then it goes and gets installed, and I have it and I can use it. But on supercomputers, this is what the installation process looks like. You have to down all 10 or 100 tarballs you need, start building, and then fight with configure and make install and all of those things for a long time. Run the code, and then it seg faults, and you start over. So the idea with Spack is that you can install lots of different configurations of software easily. On big machines, we typically care about installing for unique architectures installing for platforms that we haven't seen before. They tend to be very unique, and not all the software tends to be built there. So every installation is essentially a port. And so what Spack allows you to do is it has a syntax that lets you install the software the way you want it. So you can say Spack install MPI leaks and just get me this package. I don't care how, make sure it's installed. You can be specific about the versions. You can say what compiler you want it installed with. So you can say install with GCC at a particular version. You can say I want a particular build option. You can inject flags into the build if you want. You can say what particular microarchitecture target you want. And that's all recursive. So you can say that about dependencies too. You can say I want MPI leaks built this way. I want mpitch built this way, or I want it built with mpitch instead of OpenMPI, things like that. The idea is that you can sample the space of installations very easily. And that's what this syntax allows you to do. If you're used to other package managers, they tend to have a single recipe per build or per configuration. Spack has one recipe per package. And so these things are templated. This is an example of a Spack package. It's pure Python. It's just a simple class. It has a comment that tells you what it is. There's a homepage and a URL where to fetch it. You can download multiple versions. So this says I can build these 3 versions of this package. I can build it with MPI or OpenMP. These are options that you can put on the command line. And it depends on MPI when MPI is enabled, and it depends on CMake. And then these down here are just build instructions. So this tells you how to assemble the CMake line for installing things. And this, since the package is research software and lacks an install target, you can write it just in the package. So this is not a lot of code. It tells you how to build a CMake package in a lot of different configurations. So I think that's, there are a lot of combinations that you could build this in. So to handle all of that complexity, we don't just install into one place. Every package in Spack is installed into its own directory. So if you have a DAG like this, every configuration of that graph is installed into a hashed directory. And this is similar to Nix and other systems. Spack is a little different in that we hash the configuration. So it's really designed to build new versions of things that you haven't built before, whereas I think most other systems are designed to build something that someone has built before. And the thing that we do here is we ensure that all the packages are RPath together. So RPath is kind of like LD library path, except for it's specific to an executable or a library. So essentially we bundle where the dependencies live with the things that we install. So they already know where to find their dependencies. You don't need to have the user or whoever ends up running the code tinkering with LD library path or loading modules or things like that. We do generate modules, so you can use modules, but you don't have to. You can just run it in place and it knows where its dependencies are. And the logic behind that is, it's very frustrating to build things. You probably knew what you were doing when you built something because you had to, but the person who runs the software may not be the person who even installed it. So we don't want you to have to remember everything about these large graphs of packages when you get around to installing them. So we started this project in I guess I started it in 2013. It was just me up until about 2015 or so when more people started joining in. We presented this at Supercomputing, and then we really started getting contributions to packages. So I think around this time we had maybe 300 packages in Spack, and now we have over 4,000. We've grown to have 550 contributors and over 2,500 monthly active users worldwide. And that's based on who accesses our documentation site. This is one of these Google Analytics plots that sort of shows where all the Spack user base is. And you can see that we're getting contributions from lots of different organizations. Livermore, where I am, is really less than 10% of the total packages in terms of contributions, and other places are helping us out a lot. So we get out a lot more than we put in because we're able to leverage community effort for this stuff. We're also used on a lot of the top supercomputers just because it's easy to build for new architectures with Spack. We try to make that easy. But also, as you can see, we're hitting a pretty broad audience in the HPC community worldwide too. One of the things that we've been doing lately is we've been adding more DevOps-ish features to Spack. And so we added environments, but they're a little different from things like virtualenv or even Conda environments in that you can have a YAML file that describes what gets installed along with some configuration. So this says install these 3 packages in this environment. You could hand this to someone, they could rebuild the same environment. But we also generate a pretty detailed lock file. And this includes things like the architecture, the flags, the OS that it was built for, all the build options on the packages, and so on. So you can reproduce a build pretty exactly with this. And you can use the environments at the command line, or you can use either this YAML file, the sort of abstract description, or this lock file, the concrete description of the environment, to reproduce it. And this one will need to be resolved again, so this may differ by platform, but it will get you the same functionality. And this one is really for reproducing the exact same thing on the exact same platform later. So we've built features on top of this environments feature. We have something called Spack stacks, which I think you'll hear maybe a little bit about in the Georgia presentation, to build combinatorial stacks. You can say, I want these compilers, these MPIs, and these packages, and we will build the cross product of those things. We will build things in combinatorial ways. You can also do things like say, I want to build all these packages, both static and shared, or with some other build option, or with different combinations of flags. It's very easy to build a giant matrix of things. We have this Spack containerized feature over here, where you can take an environment and turn it into a container image for Docker or Singularity or Podman. That gives you a build recipe that you can make pretty quickly. And then we also have this GitLab CI support down here, where you can take an environment, say one of these large matrices, and just generate a GitLab pipeline to build it all in parallel in CI. And as you push to the repo, this will get rebuilt over and over again. You can make binary caches of those things, and so on. So there's a lot of sort of DevOps workflow that we—
1 minute. We're getting there. Yeah.
Okay. We're trying to make it easy to distribute optimized binaries. So we have a library that you can check out that we spun out of Spack for reasoning about microarchitectures. You can ask questions like, is Skylake compatible with Haswell, and so on. And we've recently released a new version on February 23rd that has these features and more. And then we were working on a lot of things to ease the sort of binary compatibility problem in later versions of Spack. We're working on a better dependency resolver and a whole lot of stuff around compiler runtime libraries. And we want to be able to finally have packages that can say, I just need C++ 17. Get me a C++ 17 compiler, and reason about the runtime libraries, so that the users don't have to think about messes like the fact that the Intel compiler depends on GCC and they use a particular version of libstandard C++ that needs to be common among all the compilers that you link together. So those are the kinds of things we're working on. I guess that's it. Thanks.
Thank you. Maybe I'll ask one question then.
Sure.
Anything, please. So before Chris's talk, and maybe Chris's talk might address some of this. So I'm a user of Spack, but I always feel that I'd love to have somewhere I could go where I could find sort of, as well as the bits, kind of a curated collection of quality control kind of Spack. I mean, there sort of is, but there's sort of, nobody's really, totally owned that yet, I feel. But I don't know whether there's any kind of movement in that direction from some of the big centers or anything, or.
So I guess I'll
open
say
and shared, that then one can pick up and kind of use to get going.
So it's hard to get the centers to agree on anything.
Yeah.
So there's that. And they all have sort of unique platforms in one way or another. The project under ECP that is dealing with that is E4S. I don't know if you've seen that. You can go to E4S.io.
Yeah.
They have a big set of packages that they currently build in a bunch of containers. And what we'd really like to have is them building that same set of packages across all the HPC centers, so that we could have binaries that you download.
Yeah.
And you don't have to build anything. So we're working towards that with this CI stuff and other projects that I mentioned.
Great. Thank you very much for that. That was another great talk, and kind of covering a lot of different areas of things. So that's kind of nice to see all the different things go on. So the last talk is, I think, Chris Stone from Georgia and Tech again, and he's going to talk about their software management environment. So Todd, if you can evict yourself somehow. There you go.
Right.
And then Chris, if you can share. And if you do 10 minutes, we'll be spot on the official end. So.
Excellent. Can you all hear me okay?
Yep.
All right, great. Thank you. I appreciate everyone sticking around to the end of the day. So I get the pleasure of being given the third talk from the Georgia Tech PACE group to round out our team's work here. So I'm going to be covering what we're doing regarding scientific software management at PACE. This presentation was put together by Kevin Manalo and myself. This is a team effort. You already, for those that were here earlier today, you heard a talk by Nelly and also by Sherry. So this full team effort to put all this stuff together. And so I'll kind of just get to build off of what they talked about. All right. Brief outline. I want to talk about our, I'll call it our new deployment approach to software management. For those that attended Nellie's talk earlier today, she alluded to the fact that we are migrating to moving to a new facility, but we're also coming in with some new systems. This gives us a chance to do pretty much a full refresh of our software management approach. And so I'm going to go over some of the techniques that we're doing with that, and critically how we're able to pull in 4 main tools: the LMOD, Spack combination, and then Reframe, as well as GitLab. So how we actually are able to marry those 4 different tools together. I'll wrap it up with some conclusions and hopefully lead or kind of steer us towards some future directions. And at the bottom there, I have our full team from the software team there with Kevin, Sherry, Nellie, and myself. And also this work is in collaboration with our cyber infrastructure team, Ruben, who's in charge of that. By the way, if you have any questions, please just send a chat message. I got some teammates online. We'll be able to answer them, hopefully answer your questions during while I'm speaking. So don't think you have to wait till the end. All right, so the first main topic is how we handle our software configuration. Now, we're an academic research center, a research computing facility. We have a huge amount of packages that we're asked to install. Nellie alluded to a couple hundred packages. I think she had said close to 300 packages. That's a huge amount of workload to build, install, maintain, and verify those packages. So we're really trying to streamline our workload to one, verify that we're installing what we're supposed to install, making sure that what we present to the user is functional, and we kind of limit the scope, and also to reduce our workload. We don't want to sit down and build 400 packages manually. So this is sort of a combination of, or the compendium of how we actually get to that. So to actually do our deployment, we are using Git. We're not using Git necessarily for the source code control, which we are, but we're actually using Git to maintain our actual binary installations. So instead of pushing packages out to the system, we actually each node actually does a Git pull and downloads the latest production release of our software stack. We maintain 2 branches: a testing environment and a production environment. We also use some tags to isolate certain architectural features. Now the RSEs, that is us, handle the deployment of our testing environment to sandbox systems so we can actually test things out without breaking the system. And then we work with our systems team to actually do the system-wide deployment of our production environment after we pass the verification and validation of our candidates. Now, we've got the 400 packages now installed, so we rely on LMOD modules control to actually present those packages to the users. Now, as Todd had mentioned, you can have this giant combination of MPI stack plus compiler stacks, and the actual matrices can get too big for anyone to handle. So LMOD is very nice at maintaining the hierarchy. So depending on what compiler or MPI version a user loads, they only are presented compatible packages. So instead of giving them the entire combinatorics of our package system, they only get sort of the end user packages that are supported with their current combination. Now, we also want to reduce the amount of software we have to support. So we're trying to steer users in the direction of a certain preferred compiler, as well as a certain preferred MPI version. And we're doing that by deploying a default meta module. We call it our PACE module. And we're most likely going to be doing this on an annualized basis. So we have a PACE 2020 right now, but we there's always the chance of doing a biannual update. The idea is that we sort of, unless the user takes any action, they're just automatically presented an updated module view. But advanced users can still find whatever they want. And we are using Spack, and I'm not going to get into the technical details because Todd just gave us an excellent talk on what Spack is doing. But we've used Spack to basically offload the workload for our builds. Spack is fantastic at handling a lot of the internal dependencies between packages, especially some packages just require many other packages to build, and it's too much workload to manage. So we like to think of Spack as, we don't use it for everything, but I like to think of 90% of the builds with 10% of the effort. So it's a great way to offload that the work. Overall, we're now managing 206 user visible packages, but if you think about our hierarchy, it's close to 500 modules that we actually have rolled out. 95 of those are manually built, so Spack is offloading a huge amount of that work to the RSEs to free us up to do more different work. Here's a quick view of what a user might see. At the bottom down here, at the bottom list is sort of the core modules. These would be built with the system GCC. Basically, all users are going to see this all the time. But then as you go up this table, forgive me, it's a little bit busy here. But as you go up the table, what you can see here is these would be modules that are built with an Intel compiler if they have that loaded. And then at the top here is be the Intel compiler plus a combination of a certain MPI stack. So this is the way we actually control what the user has to see. And that way it kind of limits their concern, so they don't have to worry about going and hunting down the appropriate module that they might need. We can actually split this up if you want to get a little more fine-grained. You can actually show what we've manually built, what we're allowing Spack to build, but this is going to be advanced view, and the users would never really dig into this. But it's nice to just sort of give a bit of eye candy there. So now that we've got the packages rolled out and deployed, we do want to make sure that they're actually working right. And so this is where we've integrated our V&V process for our software repository. We're using Reframe to do sanity testing, all based on regression tests. And we do this on our deployed environment as well as in our candidate packages. So we're actually using the same thing to do verification of candidates as well as continuous testing in our deployed environments. The test can be triggered either interactively by the RSE. This is great when you're just actually doing the development or builds. You can write a reframe test and test it interactively, make sure things are working. But every time we push a commit to our software repository with GitLab, it actually triggers a reframe run of that package as well as of the upstream dependencies to make sure nothing is broken. This also gives us a really quick response. That way we don't have to run the full suite. We just get a quick look that everything is still working. And then nightly we do a full regression suite. So all of our performance as well as sanity tests are run with a target of having everything done within about an hour window. Our workflow when it comes to reframe is for every user-facing or infrastructure module, we want at least one regression test within reframe. We're focusing currently on sanity testing, even though reframe also handles performance testing. Right now, we're still building out our software repository and the sanity test. So once that's done, we can kind of change our attention to performance testing. Another handy thing about adding in the full suite of regression tests is that we now have a dual for examples. So we spend the time to write these tests to verify it, but those now actually are examples that the users can look at for how to use a certain package. And we're working on some automated publication methods, so we don't actually have to curate two different versions of these examples. We'd like to be able to write once and have it populated in both reframe and in some kind of example directory. And reframe is also—
Chris, one minute, Chris.
Thank you. Reframe is also handy because it's not just an execution. It actually is doing compilation, linking, and execution. So we get a quick way of testing that the build environment and is functioning as well as the runtime environment. So our goal is a full suite. Once we're done with that, we can then turn our attention to optimization with confidence and just reframe in action. We've actually caught errors. We did a GPFS to Lustre transition, some weird file locking differences with MPI, and those were caught. It would have taken us quite a long time to dig that up. And here's a little eye candy just showing one of us did a commit of a package and it kicked off an automated test through GitLab. Some future works, we're interested in looking at some containers within our modules. Writing out those reframe tests takes a while, and so we actually think this would be a good place for some student work. The co-ops would be great for writing these user tests, and then also integrating performance testing into our regression suite, because again, we're just focusing on sanity tests right now. Wrapping it all up from our sanity tests, Spack, LMOD, great combination. These are indispensable for our work at Pace, and it's allowing us to actually focus on optimization and user engagement now, because we're no longer just building software. Thank you.
Fantastic. Thank you very much, Chris. That was a great thing. And I learned about reframe, which I hadn't heard of. I don't know whether other people did, but there was a question that Cherry answered from Todd around how sort of portable reframe is. I don't know if you, or at least your reframe spec files, you know, are they things that then one could share, or does each site have to sort of develop their own?
Conceptually, these could be shared, but there's going to be some internal configuration of what kind of runtime environment you have. They also rely on some scheduler, like if you want to actually have reframe test run through a PBS scheduler, those would have to be tuned for each site.
I see. Yeah, the usual story. Yeah, nothing's quite.
Yeah, I think a lot of the code would be reusable, but there'd be some configuration that would have to be tweaked. And Kevin would have a better idea of how to do that, though.
Excellent. Well, thank you very much. I think Sandra is itching to show us her latest Mentimeter results. Maybe, I don't know. Are you, Sandra?
Of course, of course. Yeah. Always. So let me share the screen. Yeah, so we had on the second slide 33 people who answered, and you can see 85% are from academic institutions, 3 people from national labs, and 2 nonprofit, 1 industry, and 1 other. And I'm only really a little bit interested, what is the other? This maybe.
Yeah.
Yeah. Nobody wants to, or send it to me. Yeah. That is okay.
Anyhow. So I guess a couple of things to say in closing. I should thank all the speakers. I think everybody stuck to their time very well, and the talks were actually very interesting. And I think we all learned a lot. It was a bit of a fire hose, but you know, this is the first time, you know, we've done something like this. We'll try and refine how we do it maybe. Thank you for everybody for joining. I think there are, I guess, 1 or 2 sessions tomorrow. I'm blanking now. I can't remember. Is it 1 or 2?
It's 1 session.
Just tomorrow. 1 session tomorrow,
which is going to be more interactive. There's some breakout things planned and various things, and we've not done this before, so we'll see how it goes. But we're definitely hoping people will join and be able to participate in a more kind of interactive way. I'm just going to post the US-RSE join link into the chat there, just in case anybody who was on the a call now wasn't actually part of the join group. Yeah, we'll hopefully see some people tomorrow. I'm trying to, what time is it tomorrow? Anybody got the time in front of them?
It's 12 o'clock Eastern.
12 o'clock Eastern tomorrow. So yeah, so hopefully we'll see some people tomorrow, or hear some people, or whatever. Okay, thank you very much, everybody.